All right, so today is another kind of eat your vegetables class. So we will talk a little bit more about math today, about linear vector ODEs as kind of a generalization or an extension of the scalar case that we learned about on Tuesday. And then we will start what was supposed to be today's lecture. We're slightly behind, but I think that's fine, which will go into what are called linear dynamical systems, which is where you have some system that's governed by a differential equation, but you can influence the system in some way. So you can, for example, with a battery, you can decide when you charge and how hard you charge, things like that. And there may also be some things beyond your control that can shape the evolution of the system. So, for a battery, maybe it's getting power kind of randomly coming from solar panels, depending on what's happening with the sun and the clouds. So we'll talk about that. And then I'll get into an example, which will show up in your homework, which is about sort of a simple version of Earth's climate system. Okay, so last time we talked about scalar ordinary differential equations, where the variable here, this thing x of t, is a function that takes scalars as inputs and produces scalars as outputs. And it satisfies this, this differential equation, which we learned about categorization and things like that. This thing is first order, and it is linear. And here linearity really means linear in the variable x and its derivatives. Okay, so today we will talk about vector ODEs, again, in the first order linear case. And here, the governing equation is a pretty straightforward generalization of the scalar case. So now the variable x here, rather than being a function that takes scalars and produces scalars, it also takes a scalar, but it produces an n-dimensional vector. So that's the main difference, that rather than being one function that we're looking for as the variable, we have a list of n functions that are kind of packed into a vector. And then this b thing here, well, if x is an n-dimensional vector, this matrix A here needs to be n by n. The derivative of x would again be an n-dimensional vector containing all the derivatives of each of the functions x1 through xn. And then this thing b here is again a vector, or potentially a long list of functions. And then basically here we're just writing out what this means. So we're kind of packing potentially a lot of numbers into very concise mathematical notation here. So the dimension n could be 100 or 1,000 or a million. And then this matrix A could be, a million by a million matrix. It could have, lots and lots of entries in it. But this basically, if we write it out in terms of the components or the elements of the vectors and matrices, here the variable we're just writing as functions x1 of t down through xn of t. And the b also is just a list of functions. The derivative here, dx dt, is just element-wise derivatives. We talked about this kind of yesterday in the notation section. So it's just the time derivatives of each of the functions x1 through xn. And then the matrix here, A, is n by n, and each component or element of the matrix is itself a function. Okay, so it turns out that there's a relationship between nth order linear scalar ODEs and this kind of first order linear vector ODE that we just talked about. So the general form of a linear scalar ODE of any order, so it could have any number of derivatives in it, is here. And here the notation with the parentheses n as a superscript just means the nth derivative of the function x. So x1 here would just be the first derivative of x, x2 would be the second derivative, and so on down the line. And so here, this is kind of our general form of an nth order linear scalar ODE. B here would just be a scalar function of time, for example. So if we define a new variable, a vector variable, a function that maps scalars into n-dimensional vectors, we can define it as basically a list of x and then its first n-1 derivatives. So this would go x and then dx dt, d squared x by dt squared, and then kind of on down the line until we get to the n-1 derivative, which is not the highest derivative that shows up in this equation, but it's that highest derivative minus 1, basically. Okay, so if we do that mathematical move, then we can write down the first derivative of this vector valued function z. So the first component is just x, so first derivative of that will just be the first derivative of x here, so x prime. And then the n-1 component here, well, the derivative of that is just xn, so this is dnx by dx to the n. Okay, so the first n-1 rows here represent n-1 linear equations, and they're very easy, like kind of stupidly simple. This just says that, the first derivative of x is equal to the first derivative of x. So here, this is in the kind of first row, second column. We have a 1 in that position. And so this thing would multiply basically x prime in the list of elements on the right-hand side here. Okay, and then we go on down the line, the derivative of xn minus 1, that's just xn minus 1. So these equations are very simple. And then the last equation here really is just the ODE, the nth order linear ODE that shows up in the first equation here. So it says xn on the left-hand side is the function a naught times x, all the way down through the function an minus 1 times x n minus 1. Shows up here. And then we add the element b on the far right-hand side. So then we can basically, again, pack all this complexity away in our kind of simplified matrix vector notation, and we get that the derivative of z, this new vector that we've defined that has all the derivatives of x in it, is just a function matrix A times z plus some new offset vector c, which is just the vector of a bunch of zeros with b at the bottom. Yes?
Could you explain again why those diagonal line of ones are sort of offset from the main diagonal of the matrix?
Yeah, so why is this not on the main diagonal? So if this was on the main diagonal, we would have x1, the first derivative of x over here, would be basically 1 times the first element over here, which would be x.
Okay.
So that would be defining a new differential equation that says x prime equal to x. I guess the solution of that we could write down, it would be e dx or e to the t or something like that.
Then what is in that first entry?
So this is just a 0. So anywhere that there's like blank stuff in the matrix notation that I'm using here is just zeros everywhere. Yeah. I could make it a little more explicit. It just, I don't know, it's more cluttered or whatever. But yeah, no, that's a good point. Thanks. Okay. So here is our kind of general form of the first order linear vector initial value problem. So we're given some initial time, the initial state. That is an n-dimensional vector. And then we have the governing equation is just the thing that we wrote down on the last slide. And even though this is just a very benign, straightforward generalization of the scalar case, it turns out that there is no known analytical solution for this case here. When the matrix that multiplies x is a function of time varying thing. But when this a is a constant, so just a matrix full of numbers rather than a matrix full of functions of time, then this thing has a solution which looks very similar, although we have to be a little careful here because there's a lot of complexity kind of buried in this notation. But this looks very similar to the solution that we wrote down for the scalar linear ODE case when the function a was constant. So this involves taking e to the t. Okay, this is a scalar, but a is a matrix, an n by n matrix. So here we have an exponential of a matrix. And that is not defined in the way that you might think it would be, where you just take e to the component of every component in the matrix. In fact, that is defined in a different way, and we'll talk about that. And basically, the reason for defining this operator that we call the matrix exponential is because it makes writing down the solution to equations like this clean and simple. So in MATLAB, if you want to do the exponential of every component, like the element-wise exponential of a matrix, you write exp to the m. But when you want to do this special new thing that we're going to talk about in a sec, you need to write exp m. So the m here denotes matrix exponential rather than element-wise exponential. And in Python, there's similar notation. So we're just kind of jumping right to the end here. We will write down a simpler expression for this thing here under basically the assumption that this term b is constant, and that it'll get us kind of a clean linear algebra expression for the solution of this initial value problem. But let's talk first briefly about the matrix exponential. Okay, so the first thing to note is that this thing called the matrix exponential applies only to square matrices, at least in the way that we're going to talk about it in this class. So imagine kind of arbitrary dimension, but it's n by n, right? Not n by m, so not wide or tall. And then we'll define the notation for a matrix that m squared is just equal to m times m cubed is m, and so on. And so this syntax, only parses when M is a square matrix. If it had different row and column dimensions, MM would not necessarily make sense. And then the definition of the exponential is the same, if you remember from your calculus classes, kind of the power series representation of the function e to the x or e to the t. We do the same thing here, basically, with the matrix exponential. So it's the identity matrix. So this is, again, an n by n matrix with ones down the main diagonal. And then it's the matrix M itself, 1 over 2 factorial times M squared, and then on down the line. And this is an infinite series that would go on forever. Okay, so basically the reason that we define this object, the matrix exponential, is because it has this nice property, which looks like a property of the exponential function for scalars, right? That if we take the derivative of e to the tm, we get back just m times e to the tm. And I'll walk through real quick how we can show that. So we take the definition here of e to the m, put a tm in everywhere that we see m here. Okay, so this is just e to the tm. And then take the time derivative of this. Well, the matrix M is constant, so we don't really need to worry about it when we're taking derivatives. All we need to think about is differentiating the function of time that multiplies M. So here we take the derivative of Tm. Well, that's just M, because the derivative of T is 1. Here we have 1 over 2 times T squared. Well, the derivative of that, half T squared, just becomes T. And so that's why we have a Tm squared here. And then we can proceed in that fashion, kind of term by term throughout the whole series. And then now we have this expression here. We can factor out an m. And actually, at this point, we could factor an m out either to the left, so left multiplying this matrix here, or we could factor it out to the right and have the m here instead. It turns out that either way is valid. So once we factor out the m, we again have identity, right? M times identity equals m. Here we have Tm. If we multiply that by m, we get Tm squared, and so on down the line. And then we just notice that this thing in parentheses here is exactly the definition of the matrix exponential. So I'm not going to ask you guys to prove this on homework, but this is just kind of why we get this very useful formula, and in fact, why we make this definition of the exponential. Okay. So this is the main property. I'm just summarizing it again, that if we take the time derivative of e to the tm, we can write that either as m on the left times the matrix exponential e to the tm, or we could, again, because we can do the factorization either to the left or to the right in the previous slide, we can also write that as e to the tm times the matrix m itself. And so whenever we're dealing with these kind of vector and matrix formulas, it's good to kind of remember what the dimensions of things are and make sure that the syntax parses. So here, this thing is a square matrix, and this thing is another square matrix with the same dimension. So they're both n by n. So this works out. Another property of the matrix exponential looks just like what we have with a scalar exponential. So if you take e to the 0 with a scalar 0, you get 1. And here, if we take e to a matrix full of zeros, an n by n matrix of zeros, we get the identity matrix. So that kind of straightforwardly generalizes. If we have e to the a plus b, that can be written as e to the a times e to the b. And we have a similar formula here for the matrix exponential. Basically, we get e to the t1m times e to the t2m. And this holds for any real numbers t1 and t2. And then it turns out that e to the m is always invertible. And if you take its inverse, you can show that that is equivalent to e to the negative t times m. And this, again, just looks like it's like an obvious thing. We know that e to the a, that whole thing to the power -1 would just be e to the negative a in the scalar case. And so this just looks like a direct generalization. But actually, there's some kind of sophistication built into showing that this thing works. So if we take the product e to the tm and multiply it by e to the negative tm, well, we can use this property up here to show, basically do the backwards of this property here to show that we have e to the t minus t times m. Well, t minus t, that's 0. So we have e to the 0m, 0 times any matrix. Well, that's a matrix full of zeros. And then we use this property here, e to a matrix full of zeros is identity. So here, this tells us that if we take this thing, e to the tm, multiplied by e to the negative tm, we get the identity matrix. And so that tells us that these things are inverses of each other. All right. I think just one last property, and I'm going to prove here. So if we integrate e to the tm, we again get something that looks very familiar from doing an integral with a scalar exponential function. So here we integrate this thing. We get m inverse times the difference e to the t2m, so e to the t evaluated here, minus e to the t1m. So the scalar analog of this thing would be like integrating e to the ta. You would just have 1 over a times the same function e to the ta, and then evaluate that at the limits of integration, and that would give you this thing here. And it turns out, again, we can factor to the left with the m inverse, or we can factor to the right with the m inverse, and either way is equally valid. And so I think this is like the last proofy thing I will do in these slides, but the reason that this works, basically, we can start by writing down this differential property. If we take the derivative of e to the tm, we have this. We now can integrate both sides of this equation. This equation is true, so then integrate both sides with the same limits of integration. It remains true. And here, I haven't done anything really other than just factor m. This is a constant out of the integral. And then we use the fundamental theorem of calculus. We know kind of the integral of the derivative just gives us the delta of the function. So here, that's all we've done on the left-hand side. Right-hand side, no change. And then we, let's see, multiply through by m inverse. We're told here, sort of the assumption underlying this equation is that m is invertible. So m inverse exists. So we can basically multiply left and right by m inverse. That will cancel with the m over here. And then we get our final equation. And you can do the same thing here. We factor the m out to the left, but you can factor the m out to the right as well and show that either one of these expressions works. Okay, so now after all those properties of the matrix exponential, you have what you need to basically go through the derivation of the formula here for the initial value problem with a vector ODE. And I'm going to ask you to do that for homework. You know the final formula, you know where you're going, and actually the steps in the derivation all run exactly in parallel with the steps in the derivation that I showed in the slides, kind of in careful detail for the scalar case. So all you really need to do is kind of pay attention to what is a matrix, what is a vector, what are the dimensions of things, and then use basically properties of the matrix exponential. So here's the final answer. And then, yeah, we want to follow the steps, use the properties that we just showed. And then we talked, I think at the beginning of class, kind of in the math background section, we talked about the product rule for matrix vector multiplication. And so you'll need to use that as well. All right, so that's problem number 2 on the homework. And then problem number 3 will relate to the next sort of section in the coming lecture. And I just want to write down a couple of special cases here. This one actually is useful almost all the time. So very often, the coefficient matrix A that multiplies our function x of t, the variable, very often that thing is invertible. And so in that case, this thing here, the integral with respect to t that we have here ends up being just this thing. So we have a closed form expression for it in kind of just linear algebra language. And I guess I'm not going to go through this, but if you want to know where this comes from, the proof is fairly easy. And then if the thing b here, the kind of the offset term in the linear equation is also constant, then we get an even simpler formula. Basically, b factors out of the integral here. And actually, yeah, I'm not going to go through this. So when a is not invertible, it turns out that there is another algorithmic way that you can still get the matrix exponential and the solution to the ODEs. But actually, I'm going to recommend that you use kind of a built-in software package, either in MATLAB or Python, to do that. It's kind of a pathological case, and so we don't really need to go into the details. But if you are curious about it, please take a look at the slides and go through them yourself. Okay, so questions about these 10-ish slides that we just went through before we switch to the next set? Okay. So again, not super fascinating, maybe from a DER's perspective, but this is really the kind of mathematical technology that underlies all the simulation that we're going to do going forward. Okay, So we're going to pick up basically right where we left off, talking about what are called linear dynamical systems. So we'll talk about those in continuous time, and then we'll talk about how to discretize in time. So very often when we do computer simulation of stuff, we don't have a continuous function of time that we're trying to evaluate. We might just care about the function at some discrete values, once every hour, once every minute, something like this. And so the material today will basically give equations for how to do that kind of simulation. But first, what is, so we'll go over that, and then we'll talk about how to linearize a nonlinear dynamical system. So we won't really have too many nonlinear systems in this class, but I think it's good background knowledge to know how you can deal with a nonlinear ODE and approximate it pretty well with a solution to a linear ODE. So we'll talk about linearization, time discretization, and then we'll get into a simple model of Earth's climate system, which is actually a nonlinear dynamical system, and we'll go through the steps of linearization, time discretization, et cetera, and show solutions. And then that'll be basically a homework problem, is to implement this in MATLAB or Python. So dynamical system here. So here we're dealing with, again, it looks a lot like the sort of vector linear ODE that we just talked about in the previous chunk of slides. But we have a state, typically, is kind of a variable that we're trying to evaluate. And this generally will be a function from a set of real numbers, or so takes scalars as inputs and produces vectors as outputs. And then the dimension there, nx, is the dimension of what we call the state. And t here denotes an independent variable. Almost always it will be time. And then we have kind of our linear ODE, but rather than having sort of just the one term b, here we have, which was just a vector, a lowercase b that showed up in the previous set of slides. Here we have a matrix b multiplying u, and here u denotes something that's under our control. So you can think of u as being the charging power of a battery, or maybe the heat output of a heat pump or an air conditioner, something like that. And then W basically is stuff that we don't control. So this could be things related to outdoor temperature or the amount of sunshine that we get on a solar array, something like that. So our nomenclature here, U, we call you the action or the control input. W, typically we would call the disturbance. You might also hear it referred to as the process noise, probably not by me, but that's kind of another term there, or the exogenous input, something that's kind of beyond our model, beyond our control. And then A, we call the dynamics matrix, and B here we might call the action matrix or the control matrix or the input matrix. So this is what's called a perfectly observed linear dynamical system. So dynamical, by the way, just means changing over time, and linear refers to the particular structure here. And system is like system of equations, right? So this is all matrix vector notation. It could, again, hide all the complexity of 100 or 1,000 or 1,000,000 equations. There are also what are called imperfectly observed linear dynamical systems. And so here we still have the same state equation or dynamical equation, but we also have what's called an output equation or a measurement equation. So here, y on the left-hand side is something that we're measuring or observing. We call it an output or the observation. And then we have a matrix C, typically called the observation or the measurement matrix, multiplying our state. And then we have another matrix D potentially, which is called the feed through matrix, which would multiply our action. And then we also have V here. And this could, you can think of it as like a sensor noise. If you're trying to, for example, measure electric power, and you look at, power measurements of something that is constant, typically those measurements will be kind of fuzzy looking because all sensors have some inaccuracy. So V you can think of as sensor noise. Okay, so that's kind of the full generality of a linear, time-varying, continuous time dynamical system. Yes, question.
Would it be like W describing the system creating the noise and is how the output is receiving?
So the question for folks online is there a relationship between W and V? So we call W sort of the process noise and V the output of the measurement noise. In general, you can have, so if we think of like in a signals and systems, if you specify some distributions on these things in a probabilistic kind of sense, there could be correlations between the sensor noise and the process noise potentially. but usually we think of these things as different. So in the context, I don't know, one of the first DERs we'll talk about would be buildings. So we'll talk about EVs and batteries, and then the next lecture will be about kind of the thermal behavior of buildings. So in that setting, which is familiar to me, the W here would be, for example, like heat that we get into the building from sunlight, or from body heat, or from all the electrical and lighting stuff that's running in the room. And then maybe we're measuring temperature kind of at that thermostat on the wall. So V would be sort of thermal noise related to whatever sensor is in there, a thermocouple or something like that. So in that case, there might be some vague relationship between them, but we probably wouldn't model it. But another problem, certainly you can have correlated noise. Yeah. That's a good question. Thank you. Okay, so this is kind of the full generality, the full glory. Usually we don't need kind of all this complexity. And so there are a whole lot of simplifying cases that are actually very common in practice. One is that the system is time invariant. And so that means that the matrices, A, B, C, and D, are all just matrices full of numbers. They are independent of the variable t. Often, so like in a control systems class, you would deal with SISO control, usually single input, single output. And that means basically you have one kind of action, one decision that you can make, and you're measuring one thing, one output. And then very often we have no feed through, so the matrix D is equal to 0. Again, oftentimes we have perfect observations, or at least we assume that we have perfect observations. And so there, the output is the entire state vector X with no noise. And then often we deal with deterministic systems, which means that there is no noise, no process noise, so nothing affecting the system that's beyond our control. And then our measurements or information is perfect. So no sensor noise either. And actually, most of these assumptions will be valid for like almost all the DERs that we study. So I kind of just wanted to give you the full generality, and then we'll deal mainly with the simple cases. Yes. Yeah, no, that's a very good point. So the question is, will these simplifying assumptions be valid in reality for our DERs, or only kind of in the simplified world in which we model DERs? And the answer is it's the second one. And you're totally right that when, in reality, you're dealing with a real physical system, you're measuring something, your sensor is never perfectly accurate. You never have kind of all the information you can want. Yeah, so can we remove the noise and still have a pretty good model? I think so, yes. Often you can use kind of a noise-free assumption in a real system, and even though it's not perfectly accurate, that assumption, you can still get pretty good behavior of something like a control system. But yeah, I think what I want to do, the reason that we're going to make a lot of these simplifying assumptions when studying the DERs is because I kind of want to get rid of most of the complexity and focus on giving you guys intuition for how stuff works. With the understanding that then if you want to add in, a way to account for sensor noise or some disturbances that you haven't included previously, that then you can fall back on some of this notation and hopefully figure out how to do that, or at least know where to look to learn how to do that, I guess. Does it make sense? Okay, good question. Thank you. All right, so why do we care about linear things? In reality, everything is nonlinear. But linear things typically give us tractable equations, tractable algorithms, things that can run quickly and give us useful behavior. Also, there's a relationship between nonlinear and linear things, which is linearization. This kind of gets back to the idea of Taylor series, expansions, and things like that you've probably done in other classes and other contexts. But we'll show through this example that often for nonlinear systems, you can approximate them very well with linear systems. Okay, so just a little reminder on how linearization works. And this is starting with the scalar case, which should be familiar to everyone. So suppose we have some nonlinear function f that takes scalars as inputs and produces scalars as outputs. And let's assume that it's differentiable at some point and call that point x hat. So this could be 13 or negative 21 or whatever it is. So then Taylor's theorem basically tells us that if x, the kind of unknown variable, is near this known thing x hat, then the true nonlinear function f of x is very near its linear approximation, which is f evaluated at this fixed point x hat, plus the derivative f, again, evaluated at that same point, times the difference x minus x hat. And so here's what that looks like graphically. So here I've taken a very simple function. The blue thing, this is the true nonlinear thing, could just be x squared. And then we'll pick a point, I don't know, x hat equal to 1/2. And then the linearization here, the linear approximation to f at the point x hat is just the tangent line to this curve. And so it ends up having the formula. It's very simple, just x minus 1/4. And we get that by evaluating the slope of this thing and plugging in the numbers here and so on. So this scalar linearization idea extends very naturally to the vector case. So suppose now that we have a nonlinear function f, and it's a vector, a function that maps vectors into vectors. So it eats vectors in a space Rn, and it spits out vectors in a space Rn. And those dimensions can potentially be different. And again, we assume that it's differentiable at x hat. Now, f here would be a list of functions. It would be a list of m functions, f1 through fm, all kind of stored in a column vector notation. And so here, when we assume that the vector function f is differentiable, that means each of those component functions is differentiable. Okay, so then again, there's a Taylor's theorem kind of in this higher dimensional case. And it says the same thing, basically, if our variable x is in the neighborhood of some known point x hat, then the function value, the nonlinear true function value f of x is very near the linear approximation. So rather than being a line in one dimension, this thing would be a plane in 2 dimensions or a hyperplane in higher dimensions. And so this thing here, D, is called the derivative matrix or the Jacobian matrix. And here is its definition. So again, f is just this list of functions, f1 through fm. And so the first column of the derivative or Jacobian matrix here would be the partial of f1 with respect to the first variable, x1, all evaluated at this point x hat. And then we just kind of go on down the line, doing that to each of the component functions of f. So we take the derivative of each of them with respect to x1, store them in a column. And then we do the same thing with all of the other variables until we get down to xn. Okay, so now we can apply that idea of sort of vector valued function linearization to a nonlinear dynamical system. So here, for the linear dynamical system, we had, again, a vector x here, a function that we're looking for is kind of our state vector. And then we had ax plus, bu plus w. We had the kind of simple linear form of the right-hand side here. But here we're considering a sort of general nonlinear vector ODE. So here we have a function f. Again, it's a list of a bunch of functions, n of them in this case. And it takes as inputs an nx dimensional vector, an nu dimensional vector, and an nw dimensional vector. Maps it all to a space Rnx. So we're just basically going to apply our linearization rule to f, and then write down what the derivatives of f look like for that Jacobian matrix. And then basically we will find a way to approximate this nonlinear dynamical system by a linear system. So we begin by saying, suppose that we have these are called nominal trajectories or solutions, x hat, u hat, and w hat, that satisfy the governing equation. So this function x hat, again, a vector valued function, if you take its derivative sort of anywhere along a trajectory, this derivative is equal to f evaluated at the x hat, u hat, and w hat. So then we will define what are called perturbations. So this basically is just the true thing x minus the hat thing here. And the idea here, again, it's going back to this formula here. This basically multiplies a derivative times the perturbation. And so we define perturbations not here just for the x, but also for the u and the w. Okay. Then if we're in the neighborhood, sort of our trajectory x, u, and w, the real thing that we're trying to solve for, is close to this point or trajectory defined by the hat variables, then we can write down the derivative of the perturbation of x, the state perturbation. So that's just dx by dt minus d by dt of the function x hat. Well, this dx dt, we know this comes from the underlying nonlinear ODE is given by f. and then f evaluated at the x, u, and w. And then the second term here is just, again, f, but evaluated at the nominal trajectories. Okay. So this thing, the perturbation in f, we know from our linearization rule, Taylor's theorem, that we can write this thing basically as that Jacobian or derivative matrix times a bunch of perturbations. And so the perturbations here are the del x, del u, and del w. And these matrices A, B, and G that I've defined here are just built from the partial derivatives of f, but with respect to the state variable, the action variables, and the disturbance variables. I've glossed over a few steps here. I don't necessarily want you guys to be able to implement this. I won't ask you to do it in homeworks or exams, but I want you to kind of understand where this comes from, and in particular to get at the big idea of at least some of the steps that you could use if you wanted to approximate some nonlinear function that's hard to work with a linear function. Okay, so this thing here, basically, this thing is now a linear dynamical system. We have a derivative, and the state here is the perturbation del x on the right-hand side. And then we have a linear matrix multiplied by that del x. And then we have input terms as well, related to kind of the action and disturbance perturbations. Questions about this? Okay. All right, so we will use that in a sec in the context of a simple climate model. Before we do, I want to talk about how to basically discretize in time. So the reason that we want to do this is that computers are helpful tools when we're dealing with dynamical systems, which again is the main modeling tool that we will use for DERs in this class. So we can simulate the evolution of some changing system, and we can also optimize. For example, what should we choose for the action U? Maybe the temperature set points on a thermostat, or the charging rates for an electric vehicle battery. So we can do that kind of calculation on a computer. But computers, like, they have ones and zeros. They operate typically with discrete things. And so it's easiest. It's not the only way to go about this, but one easy way to do it is to basically define discrete time steps and then evaluate your function only kind of at those sampled intervals rather than at any arbitrary time. So we do that. This is our time axis. We can, we're interested in some time span from an initial to a final time. We chunk that up into a capital K time steps. And these don't necessarily need to be the same duration. So there are some settings where you might say, behavior is going to be really smooth and boring for a while, so we'll take really long time steps. But then there's going to be a lot of action in some really exciting, fast window, and you might take a lot of time steps during that window, so you can kind of keep track of what's happening. But very often, and actually I think always in this class at least, we will assume that we have a constant time step. So we have t0, and then this is a duration delta t. T2 would be 2 delta t, and so on. Okay. So talking about time discretization here in the case of first order linear vector ODE IVPs. So these are the things that we just talked about in the previous slide deck at the beginning of this class. So if this thing here, A, is constant, we just talked about how we can write down the solution to this initial value problem using the matrix exponential. And we're doing that here. Okay, so we're not quite to the time discretization yet, but let's suppose that we have this linear dynamical system. So the difference here, the dx dt is the same, the ax is the same that we showed here, but we just had this vector b as kind of all the additive stuff in this equation. And here we have expanded that vector b into matrix b times the action or the input that we have control over, plus some disturbance term w. So if we assume that this thing here, the A, is piecewise constant over any time step. So if you're doing hourly time steps, you might allow A to change from 1 hour to the next, but within any hour, A is the same matrix, the same numbers. If that is the case, then we can just write down a formula that gives us the next state, kind of the state at the next time step, in terms of the state at the current time step, tk. And this looks like a kind of gnarly, complicated formula, but it comes from the fairly simple formula that we just showed in the last slide for the linear vector ODE system. And here we just make the observation that the vector b that showed up on the previous slide, we can write as just all the additive stuff that shows up on the right-hand side of the dynamical system kind of representation. So if you wanted to simulate a system, basically you could start with a known initial state, and then that would be t0. And then you know what a is, I guess, and you can compute the matrix exponential. So as long as we're able to do this integral here, and we'll talk about ways to do that, as long as you're able to do that, then you can start with the state at x0 and know whatever your action is, u0, and whatever disturbance is happening during that time step. And then you can just simulate forward to get the state at the next time step, x1. And then you just repeat that process and you can simulate forward through time in this kind of iterative marching fashion. And that's basically the technology that we'll use to simulate all sorts of systems, from batteries to buildings and things like that. So here's just kind of a picture of what discretization in time looks like. So we have in general a continuous time access here, and then we chunk it up into discrete time steps. And the true function may be evolving kind of in weird, wiggly ways, but we only keep track of the function value at these discrete time steps. So we'd have a finite dimensional vector that stores x at time 0, at time 1, and so on, all the way to time k. And then similarly, the action here, the input that we're doing to the system, might also be wiggly and time varying. And we only, again, keep track of it at sort of the times 0, 1, and all the way up to time k. Yes?
When you're running a simulation like this, what's a normal sort of step in time? How long would that be?
Yeah, so the question is, when you're running a simulation like this, how long of a time step should you use? Should you use an hour? Should you use a minute? Do you need to use a second or a nanosecond, right? And that really has to do with, so there's something called the Nyquist sampling theorem that I guess you probably will learn about. You're a junior or sophomore? So next year you'll probably learn about it in 365, 375. But basically it tells you how quickly you need to sample the system as a function of kind of the characteristic timescales at which the system evolves. So a thermal system, like the temperature in this room, is going to be fairly slow. So there's not going to, if you like took a measurement every nanosecond, they would be really boring. They wouldn't change very much. But over 15 minutes or 30 minutes or an hour, you would start to see real change. And so you might say, oh, I'll pick a time step that's like slow enough that it will be easy to compute with, but fast enough that I'll capture that actual evolution. So you might take 5 minutes or 15 minutes or something like that. Conversely, if you were dealing with an electrical system where kind of it evolves a lot, if you look at the voltage in a circuit or something like that, over the course of a second, it might change a whole lot. So you might take a fraction of a second, a microsecond, or something like that as your time step. So it really has to do with the physical system that you're working with for that reasons. Yep, good question. Okay, so we are almost to the point where we can write down kind of a general formula for simulating a linear dynamical system. And once we have that under our belts, then we can move on and simulate a bunch of cool DERs and other physical systems. Okay, so here, if we make the assumption that basically everything is piecewise constant, everything except the state, we allow that to evolve in kind of a general time-varying way, but we assume that all the matrices and the inputs are constant over each time step. So again, these can change from 1 hour to the next, but within any given hour, if that's our time step, they would be the same. Okay, so now we can write down our formula. It's a little bit simpler. From the last slide to this slide, all we really did was factor out all of this stuff, which is constant over the interval tk to tk plus 1. It's constant, therefore it factors out of the integral. And we're almost there. We just need a way to evaluate this integral term here. And in the case where our dynamics matrix A, which is n by n, if that is invertible, then this integral thing here, e to the ta times this integral, we have a formula for, right? So it's the inverse of A times this thing here with a matrix exponential of A, and then subtracting off the identity matrix. Okay, and here's what time discretization looks like. In this case, we're assuming that the input is sampled, or sorry, is constant over each time step. So here we have basically a stair function with u, the input. So it's constant between t0 and t1, and then we have a jump down here to some other value from t1 to t2, and then it would kind of keep jumping in weird ways until we get to the end. But the function x is smooth. It's continuous. It's not smooth. It's continuous. So it's able to kind of evolve in a weird wiggly way. But the derivative of x might have discontinuities in it. So we go from increasing to decreasing quite suddenly, for example, and that's okay. All right. So putting all that together, again, you probably don't need to remember all of the gory details of that derivation so much as the formulas that we actually use, because this will, again, be how we simulate TERs going forward. So suppose that we have this continuous time linear dynamical system. We get this from doing physics and getting governing equations for batteries, buildings, whatever we're studying. So this is the system that we're dealing with, and we assume that these A, B, and W, the tilde things here, are all constant over each time step. In that case, we get an equation that allows us to simulate our linear dynamical system. It basically says that x at k+1, where here we've used the notation where basically rather than writing t subscript k+1, we just write k+1 instead. So x at the next time is equal to a times x plus b times u plus w. And then we have formulas for what the matrices A and B and the exogenous input or disturbance W look like. The A formula is clean, so we can do matrix exponential in MATLAB or Python, so we can just evaluate this given a given A tilde. But these things still have annoying integrals in them, so we're not quite at the final formula that we want for the B and the W. But in the case where the matrix A is invertible, or A tilde here is invertible, then those integrals on the previous page simplify, and they just involve basically A inverse and again a difference A minus I. And so this is something now that you could program entirely. So first you could compute A of k, which is different from this A tilde here, right? So A of k is defined as the matrix exponential of A tilde. So first we could compute this thing. And then once we have that, now we're just doing a matrix inverse, which we can do in MATLAB or Python and multiplying it by these known matrices or vectors here. And then these three lines of code are actually the way that I would recommend getting at basically the formula. This is the ultimate thing that we want. And so you can use built-in tools in MATLAB or Python to do the calculations of the A, the B, and the W automatically, rather than having to kind of keep your hat on through building all the matrices and doing all the kind of inversion and solution and stuff like that yourself. So this code works in MATLAB. We define a continuous time linear system. SS here stands for state space. And we put in the matrices A, B, and then you can also put in C and D if there's an output equation or a measurement equation. Very often C is just the identity matrix, meaning the output Y is the same as the state X. And then D, usually you just put in a zero matrix with the appropriate dimensions. So this defines the continuous time system. And then C2D means continuous to discrete. So this does the time discretization for you, and it builds the discrete time linear system. And then if you want to extract the matrix from this discrete time system, you can just do dsys.a. So in MATLAB, this is basically a struct, and this gets you a field in the struct, which would be this A matrix. And you can do the same with B or whatever you need. So I think a good exercise would be write down some simple system and go through the steps of discretizing, and write down these matrices yourself, and then confirm that you get the same thing that you do with these built-in functions, either in MATLAB or Python. And I think Python also has a C2D function. So if your stuff agrees with the built-in stuff, then you can be pretty confident that you understand how to build all the matrices and do all the calculations. Okay, so that's for the linear case. You might also ask, okay, what about the nonlinear case? How do we go from a continuous time system to this kind of easy to work with discrete time representation? And it turns out that there is no analytical formula like the one that we derived today for the linear case for the nonlinear case. So if you have a general kind of nonlinear dynamical system here in this representation, and you want to write code that works for any arbitrary function f, it turns out that there's no way to sort of just write down what that looks like. Nonlinear ODEs are hard to solve, basically. Hard to solve with pencil and paper. But we have algorithms, basically computational methods for solving ODEs that work very well for nonlinear systems. There's a famous and very good, very efficient one called the Runge-Kutta fourth order method. There are a bunch of other methods that are better potentially for special problem classes, but this is kind of a workhorse method that's good for a wide range of problems. And so here is MATLAB syntax, but again, Python syntax looks fairly similar, and there are built-in functions for this in Python or Julia as well. But so if we assume that this function f of x, u, and w has this particular form, there's nothing special about this form. I just wrote down something kind of simple and nonlinear so that we could give an example of how to program it in MATLAB. So first we would define, this is what's called an anonymous function. It basically just says f, this thing is a function. You give it two inputs, a time and a state, and it gives you back basically this thing here. So here u and w are basically data in this function. They'd be parameters defined inside the function, and then x is the variable that we feed to the function. And so this thing just returns the product x times u to the w. And then here is the solver, ODE45 is the MATLAB function that does the Runge-Kutta fourth order method. So we take our function, that's basically the right-hand side function that shows up here. We plug that in, we give it the initial time and the final time that we're worried about or interested in. And then we give the initial state, so the state at time tk. And then this thing under the hood does some very clever calculations to basically integrate forward from the initial state x to the final state x, initial state xk to the final state xk plus 1. And then at the end, you can extract your xk plus 1 as just the object solution here, the last element of that object. And in MATLAB, the syntax, if you call it with a tilde in some argument, it basically says, I don't need that argument, don't bother returning it to me. So this ODE45 normally would return, I think, a vector of time steps and then a vector of state values. And we don't really care about the time steps because we know what the final time is. If that makes sense. Yes. This right here is an @ symbol. Yes. Okay, so we went through a lot of techniques today. And I don't expect that, in the last 30 minutes that you've internalized all the gory details, but you'll get a chance to play with some of this stuff in the homework, which is due next week, Wednesday. And the context in which we will play around with these formulas in the homework is a simple climate model, which ends up being a nonlinear dynamical system. So we'll do the linearization game, and then we'll do the time discretization game, and we'll compare kind of the full nonlinear solution to the simplified linear solution. Along the way, I don't know, who has taken a class on climate modeling? Me either, right? So I had to learn a little bit about the basics of climate modeling in order to build this example. But I think it's interesting, and climate provides a lot of motivation for what we do in this class. So I think it's kind of fun and interesting to go through. Okay, so here's an illustration of a very simple model of Earth's temperature dynamics. Okay, extremely simple, right? So in reality, climate models are extremely complex, high-dimensional, nonlinear. They run on supercomputers. There are many research groups who've developed many versions of them, and they compare model inputs and outputs to each other to sort of calibrate things and fine-tune parameters and assumptions and all this stuff. It's a large dynamic field that's been going on for decades, and what I'm showing you here is only the tiniest sliver to just give a little bit of intuition for how these things work. But basically, we keep track of two things. We keep track of the temperature of the atmosphere, and we model the atmosphere in this very simple case as just one layer. So there's the Earth, and then some height above the Earth, there's the atmosphere, and it's just an infinitely thin little kind of shell around the Earth. And then the Earth's surface, we model as just water. So forget about land, trees, humans, animals, everything else, mountains, etc. And we just say the surface of the Earth is 70 meters basically of water that covers the entire surface. And here I'm drawing this in kind of a 1D way, but you can imagine all of this being spherical. Right? And then we keep track of energy flows, basically coming from the sun, and then energy that goes out back into space from the Earth, and so forth. So here, the orange arrows represent shortwave radiation. So basically sunlight, visible light, and also near visible wavelengths. And then red is long wave radiation, also known as thermal radiation or black body radiation. So if you've taken a class in heat transfer, or maybe a modern physics class, you've probably seen long wave radiation or thermal radiation, black body radiation before. If you haven't, that's okay too. The thing to know basically is that everything that is above absolute zero temperature always radiates some energy via thermal radiation. And so my body is radiating heat, but also all the stuff around me, your bodies, the walls, the windows, etc., are also radiating energy. And so there's constant radiant exchange between every kind of pair of objects that can see each other. And so that's true of the atmosphere. It's true of the Earth. In fact, it's true of the sun. That's really the source of the sunlight that we get at Earth. So I think that's basically what we need to know about that. Okay, so the model, we're going to go through the equations and keep track of this, but basically sunlight comes to the atmosphere. Some of it is reflected by the atmosphere. Some more of it transmits through the atmosphere and hits the Earth's surface. We assume that it's absorbed there. The atmosphere is at some temperature above absolute zero, so it radiates thermally out into space. It also radiates thermally down to Earth. And then the Earth as well, again, is at not absolute zero temperature, so it radiates thermally, and some of that goes up to the atmosphere. Some of it is absorbed here, and some of it is transmitted. So we're just going to kind of carefully keep track of these energy flows, and we're going to write down governing equations for the temperature of the atmosphere and the temperature of the Earth. And then we're going to show how those things vary with some of the different parameters that show up here. So the parameters here, R is the radius of the Earth. That's what shows up as the R squared here. S is what's called the solar constant, and it's the power intensity, so the power per unit area of sunlight that the Earth receives from the sun through space. Alpha is called the albedo of the atmosphere, basically how shiny the atmosphere is. So alpha is the fraction of this incident sunlight that bounces back into space. And then 1 minus alpha is the fraction that comes down to the Earth's surface. Epsilon here is called the emissivity or the thermal emissivity of the atmosphere. So basically defines how much of this thermal energy that comes through here is absorbed by the atmosphere. And then sigma is a physical constant called the Stefan-Boltzmann constant. So the underlying assumptions here, again, is that the atmosphere is very thin and it has essentially negligible mass or negligible heat storage capacity. And under that assumption, it basically says that the temperature of the atmosphere responds instantly to changes in forcing. And then we'll assume that the Earth's surface, again, is kind of a chunk of water that covers the entire Earth. Sorry, 70% of the Earth's surface. This is about the fraction that the oceans cover. The remaining 30% is land and ice. And then the internal energy, so for folks who have taken thermodynamics recently, the internal energy U of an incompressible substance, water is well modeled as that, is just the capacitance C times the temperature T, where we're assuming zero energy at absolute zero temperature. And this thermal capacitance here is equal to the mass times the specific heat of water. And the mass we can write as the density times the volume. And the volume we can write as the surface area of the Earth, which is related to the radius of the Earth, like this, times the depth of the water that we're modeling. And so if you run all those numbers, you get about 1 times 10 to the 23 joules per Kelvin for the thermal capacitance of the Earth. And that would multiply by the temperature in Kelvin, and that would give us a number, an energy number. That's basically the energy content of all this water. So questions about the assumptions here? All right. So now we're going to march forward with basically two sort of conservation of energy type balances, one on the atmosphere and one on the surface of the Earth. And that's going to give us the governing equations. So for the atmosphere, we do basically power in is equal to power out. So we basically look for all the arrows pointing into the atmosphere and add all those up, and then take all the arrows pointing out of the atmosphere and add all those up and set them equal to each other. So everything coming in is sunlight from space, plus some long wave radiation coming back up from Earth. So we get pi r squared times the sum s from this term, plus 4 sigma t to the fourth, which comes from this term here. And then on the right-hand side, we look for everything that's coming out. So we have an alpha s up here. We have a 1 minus alpha s down here. Those are these two terms. And then we have sort of a 4 ta to the fourth coming out here and another 4 coming out down here. That's what gives us the 8 epsilon sigma ta to the fourth. And then this term here is basically what we're re-radiating to space as thermal radiation from the atmosphere. So that's the last term here. Okay, so there's lots of symbols in this equation, but it turns out that it's just carnage. Mathematically, a whole bunch of stuff dies off. So we have an s over here multiplying pi r squared. Here we have the same factor pi r squared on the right-hand side, so those will cancel, those coefficients. We have an alpha s plus a 1 minus alpha s. So the minus alpha and the alpha are going to cancel, and we're left just with s over here on the right-hand side. We have an s on the left-hand side, so those are going to cancel. So that leaves us with 4 sigma t to the fourth over here, and then just these remaining terms over here. We have a 4 sigma t to the fourth from this coefficient, so that's going to cancel over here. So now everything on the left-hand side has died off, and all we have left is the negative 4 epsilon t to the fourth here, and the 8 epsilon sigma t a to the fourth over here. So if we move that negative epsilon term to the right-hand side, and cancel some more stuff, we get the final relationship here, which is that if we look at the fourth power of the atmosphere temperature, it's just equal to the fourth power of the Earth's surface temperature divided by 2. So if the Earth is at, I don't know, 300 Kelvin, then the atmosphere would be at 150. Oh, sorry, no, that's wrong. It would be 300 to the fourth divided by 2. Okay, so this is the result of our power balance on the atmosphere. We will take this, tuck it in our back pocket, and then use it in a couple more steps when we do an energy balance on the Earth's surface, and use it to simplify the equations that come out of that second balance. Any questions about this one first? Yes.
Super quick, why are we looking at the fourth power of temperature again? They're heading with units back, but
yeah. So why are we dealing with fourth powers? So this comes from what's called the Stefan Boltzmann law, and if you haven't taken a heat transfer class yet, that's fine. But basically, the amount of energy that any body radiates is proportional to the fourth power of its temperature. So rather than a linear thing, it's a fourth power thing. Okay. All right, so again, we're going to do a conservation of energy balance, and we're going to do it now on all the water on the Earth's surface. And so rather than a steady state balance, which would say just the power in is equal to the power out, we will also allow the temperature to change, and that will change kind of the energy that's stored in all of that water. So we have the rate of change of the energy stored in this kind of slug of water is equal to the power that it's receiving minus the power that it's giving back. So again, we wrote down the energy is U, and we have an expression CT for that. So this is just the time derivative of the stored energy. And on the right-hand side, everywhere there's a pi r squared, we have kind of this 1 minus alpha s term coming in. We have epsilon sigma t a to the fourth coming in, and then we have this additional t to the fourth term going out. So U we can write in terms of T. The thermal capacitance C is a constant. That's a physical constant related to the energy storage capacity of the water. So we get dt, temperature, by dt, time on the left-hand side, and we divide it through by the C here. And then everything else on the right-hand side is the same. We've just kind of collected terms here. And here in this equation, so we haven't changed this, but we have plugged in the result from the atmosphere power balance, the relationship between the powers of temperature there. So we replaced TA basically by, sorry, TA to the fourth by T to the fourth divided by 2. So that's where this negative epsilon divided by 2 comes from. Okay, so here, if we look at the state variable and define that as the temperature, then and an action variable, we'll talk about what we can interpret there, and maybe a disturbance variable as well. Talk about that in a sec. But basically, we have a derivative of the state variable temperature on the left-hand side, and on the right-hand side, we have a nonlinear function of temperature. So you can see how this is kind of a simple version of a nonlinear dynamical system. All right, so when we're doing climate modeling, we think about how we use climate models. Typically, they're used to evaluate what the impacts of different policies and technologies might be, on emissions and then on temperatures, and then even taking that further to impacts on human systems. So in order to do that, we need a way to basically try to quantify, in this model, what is our action? What is the thing that we have some control over by controlling how much greenhouse gases we emit? And it turns out that that thing is the emissivity E. So if we change the concentration of CO2 in the atmosphere, we change basically this ratio of how much energy it absorbs and re-emits when it's interacting both with the Earth and with space. Okay, so in steady state, meaning set the derivative here on the left-hand side equal to 0, we can solve for temperature as a function of this epsilon, alpha, and so forth. And we get a particular value for it. It has to do with the fourth root and so on. So we can plug in different values of epsilon to see what effect it has on surface temperature. So if epsilon was equal to 0, meaning we basically have no atmosphere, you solve for this thing and you get a temperature of about -4 Fahrenheit or -18 Celsius. And this would be the global and annual average temperature over the surface of the Earth. So this is like how cold it was outside during the terrible cold snap that we had over the last week or so. So this is like just totally frigid ice planet, basically the planet Hoth from Star Wars. And then if epsilon is equal to 1, meaning, I don't know, we have a crazy absorbent atmosphere, kind of like Venus does, then we get a temperature of about 30 degrees Celsius, which is about as hot as it gets here. It's maybe 90 Fahrenheit, something like that. So this is essentially unlivable. Again, this is the seasonal average and the spatial average temperature. So different places on Earth would be far hotter than 30 Celsius. So this basically is apocalyptic. Before people started emitting significant amounts of carbon dioxide to the atmosphere, kind of the pre-industrial average temperature was about 13.7 degrees Celsius. And that corresponds to an atmospheric emissivity of about 0.75. And then if we look at where we were in 2022, we have risen about 1.3, something like that, degrees Celsius relative to pre-industrial times. And so that corresponds to a higher emissivity of about 0.77. So here's a graph of what that dependence looks like. On the x-axis, we have CO2 concentration, and then two y-axes. The blue axis here is emissivity of the Earth. The orange axis is the global average surface temperature. And so you can see from 1880 to 2022, we increased the concentration of CO2 quite a bit, and that increased temperature, but it also led to this increase in the emissivity of the atmosphere, at least in this simple climate model. Make sense? Any questions about this? Yes.
So the emissivity and the temperature are both trending upwards, but at different slopes. Does that have to do with the fourth power?
Yeah, exactly. Yeah, the difference in slopes here has to do with the fourth power in this equation. So T, if we wanted a relationship between the two, there would be like a fourth root and a 1 over epsilon thing in there. So it's not quite a linear relationship. It just looks kind of linear. Yeah. Okay. So in the last couple of minutes here, I just want to kind of tee up the homework that you guys are going to work on this week. So the basic idea, we have a nonlinear dynamical system. We can do some algebra to simplify things, define the state as the temperature, define this coefficient beta, has no particular physical meaning. I'm just packing a bunch of the other symbols away into kind of one constant. And then we have a nonlinear differential equation, which has a disturbance term in it. Again, nothing particular physical about this, just mathematical convenience, packing a bunch of stuff into one term. And then we have a product of u times x, and x is raised to the fourth power. So this is nonlinear for two reasons. One is we're multiplying u and x, and another is we're raising x to the fourth power. So this is our nonlinear dynamical system. And we have defined the action here as the emissivity. And this is a proxy or a stand-in for CO2 emissions, or the concentration of CO2 in the atmosphere. Okay, so then we can linearize this thing, basically using the equations that we wrote down. I'm not going to go through these today, but I encourage you, as you're like trying to make sense of what's happening in the homework, to look at this slide and to look back about a dozen slides when we showed the math of why we're doing what we're doing here. But the punchline basically is that we can write down a linear dynamical system that approximates pretty well the nonlinear dynamical system that showed up on the last slide. So here's our linear system. And then we can do our time discretization for both the nonlinear and the linear system, although using different methods. And so we write down our discrete time version of the linearized system. And then you can take this and program it in your computer and make graphs basically under different boundary conditions. So here in each of these graphs, the black dashed line is the nominal trajectories. So this is for the full nonlinear system, assuming basically no human intervention. We kind of just do business as usual with greenhouse gas emissions. So then CO2 concentration goes up linearly over time. This is basically today through 2100. Concentration goes up. And then blue is what we're simulating as a true scenario. So we're modeling basically slower CO2 emissions out through 2100. So rather than increasing the atmospheric emissivity like this, with high CO2 emissions, we have somewhat lower CO2 emissions, bringing us on kind of a flatter trajectory. And then in the code that you guys can find on GitHub, sort of adjust this atmospheric albedo. Again, nothing particularly physically representative about this. I just wanted there to be some disturbance, something that's beyond our control. So here we're imagining the amount of sunlight that the atmosphere reflects varies kind of sinusoidally over time. And then the magenta dots here are the solution that comes out of our linearized system. So the horizontal axis here is the global average surface temperature, the temperature of all that water on the surface, basically. So you can see it goes up in the nominal scenario where we're not reducing emissions much. It goes up kind of linearly. And then due to this sinusoidal variation up here, in the true scenario, with that disturbance, we're getting a kind of sinusoidal thing. And we also get less temperature rise in this scenario than we get in the nominal scenario. And then the thing to note is that the magenta dots lie right on top of the blue curve here. And if we zoom in and we look at the difference between those two, we look at the error. So this is the linearized solution minus the full nonlinear solution. We see that error starts out basically at 0. We initialize with the correct initial state, and then it increases in magnitude over time. But the x-axis here is in units of 10 to the minus 3. So we're staying within basically a few thousandths of a degree Celsius of the true solution. So the message here is basically, if you're careful about how you do the linearization and the time discretization, you can get basically a good approximation of the nonlinear dynamics, at least in this problem, with a linear system. This is trying to kind of convince you that from here on out, we're going to deal mainly with the linear systems. But if you wanted to deal with a nonlinear system, you kind of have a lot of machinery that can be useful in that case as well. Okay. So I will stop there. I'm a little bit over time. If anybody wants to hang and ask a couple of questions, you're welcome to. But if you need to take off, please feel free.